I've always found the elegance of the universe fascinating. Let me show you something.
You want to be afraid, I can tell. You walked in here, you saw the title, and somewhere in the back of your mind you thought, this is the part where someone explains the most terrifying thing humans ever built, and I'm supposed to nod and feel somber about it. I'm not going to do that. Not because it isn't serious, it is. Not because the destruction isn't real. God, it's real. But I'm going to tell you something that most people never get around to saying out loud. The reason nuclear weapons work is one of the most breathtaking stories in all of physics. And if you walk out of here only knowing how to be scared, then I've failed you. Fear without understanding is just noise. Understanding, even of terrible things, that's something else. That's what separates us from every other animal that ever walked on this planet. So let me ask you a question, a really simple one. Ready? Where does the energy come from? I mean it. Right now, sitting in that chair, you know that a nuclear bomb releases an enormous amount of energy. You've heard the numbers. You've seen the pictures. Hiroshima, the mushroom cloud, the glass that fused into the ground. But where did that energy come from? What was it before the bomb went off? Was it hiding somewhere? Was it waiting? Because here's the thing, energy doesn't appear from nothing. That's not a rule I made up. That's as firm a law as anything we've ever discovered. Energy is conserved. It doesn't get created and it doesn't get destroyed. So where was that energy before the explosion? The answer is hiding in one of the most beautiful equations ever written. And I don't just say that because it's famous. I say it because once you really understand what it means, not the formula written on a blackboard, but what it is actually saying about the universe, you'll feel something shift in the way you see matter itself. E equals mc squared. Now wait, don't glaze over. I see it already. And some of you hear that equation and you think, yes, yes, famous Einstein, I know this one. You don't know it. You know the label. That's different. Let me tell you what it actually says. It says that mass, the stuff that things are made of, the property that makes your chair resist when you try to push it, mass is a form of stored energy, not a container for energy, not something that can be converted into energy like water turning into steam. Mass is energy. They are the same thing expressed in different units, and the exchange rate between them, the number that converts one into the other, is c squared, the speed of light multiplied by itself. Now, the speed of light is about 300 million meters per second. That's already a staggering number. When you square it, you get approximately 90 quadrillion meters squared per second squared. That number, that conversion factor, is almost incomprehensibly large. It means that even a tiny, tiny amount of mass, we're talking about a fraction of a gram, contains an amount of energy that would power a city. And this is where I want you to sit with something uncomfortable for a moment. You, right now, sitting in that chair, are made of matter, and all of that matter contains energy, an enormous, city-powering, mountain-flattening amount of stored energy. The reason you're not exploding, the reason I'm not exploding, is that we are in an extremely stable arrangement of atoms, and releasing that stored energy would require processes that don't happen spontaneously under normal conditions. You are, in a very real sense, a slow bomb that never goes off. And a nuclear weapon is a fast bomb that does. The question is, what makes it go off? What process is it that actually releases that energy? Here is where the story gets really interesting, because it turns out there are two completely different ways to unlock the energy hiding in matter, and they look like opposites, but they come from the same root. One is called fission, one is called fusion. And to understand either of them, I need to tell you about something that is, in my opinion, one of the most underrated discoveries in the history of science. The nucleus. Every atom has a nucleus at its center, a tiny, dense core made of protons and neutrons packed together. And I mean tiny. If you took an atom and blew it up to the size of a football stadium, the nucleus would be a marble sitting at the center of the field. Everything else, the electrons, the orbitals, all the chemistry, happens out in the enormous empty space around it. The nucleus is where almost all the mass lives, and therefore where almost all the stored energy lives. Now here's the puzzle. Protons have positive electric charge. And what does every student learn about electric charges in their first physics class? Like charges repel each other. So how on earth do you pack multiple protons into a space the size of a marble without them blasting each other apart? The electric repulsion between two protons at nuclear distances is enormous. It should be unstable. It should fly apart immediately, but it doesn't. Why not? Because there is another force in nature that almost nobody talks about in popular science, even though it is absolutely fundamental. We call it the strong nuclear force, and it does exactly what the name suggests. It is strong, ferociously strong, stronger than electromagnetic repulsion at very short range. When protons and neutrons are very close together, nuclear close, marble close, the strong force grabs them and holds them like the most powerful glue imaginable. So you have this competition happening in every nucleus in the universe. The strong force pulling inward, trying to keep everything together. The electromagnetic force pushing outward, trying to blast the protons apart. And in stable atoms, the strong force wins. The nucleus holds together. Everything is fine. But, and here is the first beautiful surprise, the strong force has a range. It's only effective over very short distances. And this creates a problem for large nuclei. Think about it like this. Imagine you're stacking magnets. The first few stick together fine. The magnetic attraction between neighboring magnets keeps everything snug. But as you pile on more and more magnets, the ones at the far end of the pile start to only feel the repulsion from the ones right next to them, while getting very little of the attractive pull from the magnets at the other end. At some point, the pile becomes unstable. You add one more, and the whole thing flies apart. That's essentially what happens in heavy nuclei. Elements like uranium and plutonium have so many protons, 92 and 94 respectively, that the electromagnetic repulsion building up from all those positive charges starts to overwhelm the strong force holding everything together. The nucleus is still stable enough to exist, but barely. It's living on the edge. And if you disturb it, if you drop in one additional neutron, the whole arrangement can become untenable. The nucleus wobbles, elongates like a water droplet, and then the electromagnetic repulsion across the elongated middle overcomes the strong force holding the two ends together, and snap, it splits. That's fission. When uranium-235 absorbs a neutron and splits, it breaks into two smaller nuclei, typically something like barium and krypton, plus 2 or 3 free neutrons, plus a tremendous release of energy. And here's where Einstein re-enters the picture, because where does that energy come from? Mass. When you add up the mass of the two daughter nuclei and the neutrons, you get a smaller number than the mass of the original uranium nucleus. Some mass has vanished. That missing mass, we're talking about a fraction of a percent of the total, has become energy via E equals mc squared. And because c squared is so enormous, even that tiny fraction of a percent of mass translates into a spectacular explosion. But here's what really makes it a bomb, and not just a single fission event. Those 2 or 3 free neutrons that were released, they go on to hit other uranium nuclei, which split, which release more neutrons, which hit more nuclei, which split, which release more neutrons. A chain reaction. In a fraction of a millisecond, you go from one nucleus splitting to millions to billions to essentially every fissile nucleus in the material splitting in a cascade. The energy release is not linear, it's exponential, it's an avalanche, it's a process that feeds itself, and once it starts above a certain critical mass, the amount needed to ensure those neutrons hit more nuclei than escape, it cannot be stopped until the fuel is exhausted. And now I want to tell you about something that happened in December of 1942, because I think it's one of the most quietly remarkable moments in human history, and most people don't know the details. Enrico Fermi, Italian physicist, brilliant beyond description, one of the sharpest minds the 20th century produced. He had come to America fleeing fascism, and he was working at the University of Chicago, specifically in a converted squash court under the west stands of Stagg Field, which is a detail I find wonderfully absurd. The first artificial nuclear reactor was built in a squash court, not a gleaming laboratory, a squash court. Fermi had assembled his team. They had constructed what they called Chicago Pile 1, a stack of graphite blocks and uranium arranged in careful layers, designed so that a controlled chain reaction could be initiated and then, crucially, stopped. The graphite was there to slow down the neutrons, make them more likely to be absorbed by uranium nuclei, and cause fission rather than passing right through. The control rods were made of cadmium, which absorbs neutrons voraciously. You slide them in, you stop the reaction. On December 2nd, 1942, Fermi's team carefully, incrementally, with agonizing patience, withdrew the control rods, and the reaction started. The first sustained controlled nuclear chain reaction in history occurred under a squash court in Chicago, in almost total secrecy, with a few dozen scientists watching instruments and trying to remain calm. The only message sent to inform the project's leadership that the experiment had succeeded was a coded phone call. The Italian navigator has just landed in the New World, and the person on the other end of the line asked, "How were the natives?" And the reply was, "Very friendly." I love that. I love the restraint of it. These people had just, for the first time in the history of the universe, as far as we know, deliberately initiated a self-sustaining chain reaction in a pile of rock. They'd harnessed a process that the sun uses, and the report was very friendly. That's science. That's the real culture of science. Not triumphalism, not terror, just it worked, and we're telling you about it. Now, I want to switch gears because I promised you 2 ways to unlock the energy in matter, and fission is only one. The other is fusion, and fusion is in some ways even more beautiful, and it's the process that powers the sun, and it's the process behind the hydrogen bomb, which is more powerful by orders of magnitude than the fission bombs dropped on Japan. Fusion is the opposite of fission, in the naive description. Instead of splitting heavy nuclei apart, you push light nuclei together. You take hydrogen, the simplest element, 1 proton, in special heavy isotopic forms called deuterium and tritium, and you force them together until they fuse into helium, releasing a neutron and an enormous amount of energy in the process. But here's where I need to stop you and fix a misconception you probably have because the word opposite is misleading. Fission works because very heavy nuclei are unstable. They have more mass than the smaller nuclei they split into, and the difference becomes energy. Fusion works because very light nuclei are also, in a sense, unstable in the other direction. 2 hydrogen nuclei fused together into helium have less mass than the 2 separate hydrogens, and that difference also becomes energy. The reason both processes release energy is the same underlying reason. There is a sweet spot in the periodic table around iron where nuclei are most stable, where the binding energy per nucleon is highest. Go heavier than iron and you can release energy by splitting. Go lighter than iron and you can release energy by fusing. Iron is the ash of nuclear burning. It's the most stable nucleus. You cannot extract energy from iron by either fission or fusion. This is why dying stars, stars that have burned through all their lighter fuel, end their lives by developing iron cores. And when enough iron accumulates, the star can no longer sustain itself against gravity, and it collapses. And that collapse triggers one of the most violent events in the universe, a supernova. We are connected to this. Every iron atom in your blood was forged in the core of a star that later exploded. Every heavy element heavier than iron, gold, uranium, lead, tin, was formed in the violent aftermath of a supernova or in the collision of neutron stars, events of almost incomprehensible violence happening in the darkness between galaxies billions of years ago. The same physics that makes a nuclear weapon work is the physics that built you. You are the ash of dead stars, and the energy we're talking about today is the energy that built every atom in your body. I want to sit with that for a moment, really sit with it. Now, there is something about this subject, something specific and strange, that I think is almost never said clearly, and I feel like it needs to be said. The energy in a nuclear weapon is not some exotic alien energy brought in from outside the normal laws of nature. It is the same energy that holds matter together. It is the binding energy of the nucleus, which is the same thing as saying it is the energy of the strong nuclear force, which is to say it is one of the 4 fundamental forces that have governed the universe since the first second after the Big Bang. You are not releasing something alien when you detonate a nuclear weapon. You are releasing the fundamental energy of reality itself. This is, to me, philosophically important. We often talk about nuclear weapons as if they represent some crossing of a line, some place where humanity ventured into forbidden territory and touched something that should not have been touched. And I understand that feeling. The destruction is real and the moral weight is immense, and I would never trivialize that. But from the perspective of physics, from the perspective of what is actually happening, a nuclear bomb is just the strong force being briefly violently undone. It is the universe briefly revealing what it had always been hiding inside every atom since the beginning of time. The knowledge was always there, the energy was always there, the universe was always this way. We just didn't know it. And here is the part that genuinely keeps me up at night, not from fear, but from wonder. We can explain fission. We have excellent equations for it. We understand the binding energy curve. We understand the chain reaction. We understand critical mass, neutron cross-sections, the cascade dynamics. We can calculate it to extraordinary precision. Good. But the strong force itself? Why is it the strength it is? Why does it have the range it has? Why does the universe have these 4 forces and not 3 or 5 or 17? We don't know. We have a description, an extraordinary mathematical description called quantum chromodynamics that tells us exactly how the strong force works in terms of quarks and gluons. But why the universe chose these particular rules, why the constants of nature have the values they have, I genuinely do not know. Nobody does. And here's what I find so remarkable about that. The most powerful weapon ever built by human hands works because of a force we can describe precisely but cannot explain fundamentally. We know how, we do not know why, and somehow the universe went ahead and made itself this way without consulting us, and we stumbled onto it, and now we have to live with both the knowledge and the responsibility. Let me tell you about a thought experiment that I find useful for putting the scale of nuclear energy in perspective, because I think numbers alone don't do the job. Numbers are too abstract. You hear the Hiroshima bomb released energy equivalent to 15,000 tons of TNT, and your brain just nods and moves on. That's too much. You can't actually feel that. So here's a different way to think about it. The Hiroshima bomb, little boy, was made from about 64 kilograms of uranium. Of that 64 kilograms, only about 700 grams actually underwent fission. Most of the uranium was blown away before it could react, which makes fission bombs terribly inefficient by the standards of later designs. 700 grams, less than 1.5 pounds of uranium actually fissioned. Of that 700 grams of uranium, approximately 0.7 grams, less than a single paperclip, was converted from mass into energy. Less than 1 paperclip. That's what destroyed a city of 350,000 people, killed 70,000 instantly, and left shadows burned into stone where people had been standing. Now, I want you to think about why that should make you feel wonder and not just horror, because the wonder is this: the universe is telling you something about what matter is. Matter is not just passive stuff. Matter is not just the inert raw material that the universe happens to be made of. Matter is compressed energy of an almost unimaginable density. The chair you are sitting on contains enough compressed energy to power every electrical device on Earth for years. The energy locked in a glass of water, if you could release it entirely, would be comparable to a hydrogen bomb. We don't release it. We can't release it. There's no process we know of that converts ordinary matter entirely into energy in a controlled way. But the potential is there. The universe arranged itself so that ordinary matter is a kind of cosmic battery, and we found the partial unlock, the imperfect key, and the consequences of that discovery have been the defining challenge of our civilization since 1945. Now, I want to tell you about the hydrogen bomb, because it's a step further into the physics, and it illuminates something that I think is genuinely astonishing. A hydrogen bomb, a thermonuclear weapon, uses a fission bomb as merely its trigger. The fission explosion generates temperatures of tens of millions of degrees, which is hot enough to initiate fusion in a secondary stage of deuterium and tritium. The energy released by fusion then can be used to compress and fission more uranium or plutonium, which releases more neutrons, which can initiate more fusion, a staged cascading process where fission and fusion alternate in a chain of escalating violence. The physics of this is, in the cold abstract, extraordinarily elegant. You are essentially replicating, in a fraction of a second, the processes that occur in stellar cores and stellar explosions, in the hearts of stars and the deaths of stars. The sun runs on fusion at its core at temperatures of around 15 million degrees Celsius. A thermonuclear weapon achieves temperatures of 100 million degrees or more in the detonation, hotter than the sun's core, for a brief, catastrophic instant. Think about that. For a moment in the space of that explosion, we create conditions more extreme than those inside the sun. And this is where I want to connect you to something that, when I really think about it, fills me with a feeling I can only describe as vertigo. Not unpleasant vertigo, cosmic vertigo. The atoms in a nuclear weapon, the uranium, the plutonium, the tritium, are themselves the products of nuclear reactions in earlier stars. The fissile uranium in a bomb was created when a massive star died, and the supernova's energetic neutron flood transmuted lighter elements into heavy ones. And now, billions of years later, after that uranium drifted through space, collected into the Earth, was mined from the ground, refined, machined into precise shapes, we use it to very briefly recreate in a tiny volume something like the violence of that original stellar death. The bomb is, in a strange way, returning the uranium to the conditions of its birth. I'm not sure what to do with that thought. I've sat with it for years. There's something there about the cyclical nature of violence in the universe, or maybe about the way information flows forward in time through matter itself. I don't know. But it seems important. There's another piece of this that I haven't mentioned yet, and it connects to something I think is genuinely mysterious and underappreciated. The question of why nuclear reactions release so much more energy than chemical reactions. When you burn coal or gasoline, a chemical reaction, you are breaking and forming chemical bonds, which are the bonds between atoms in molecules. Those bonds are held together by the electromagnetic force acting between electrons and atomic nuclei. The energies involved are measured in electron volts, a few electron volts per reaction event. When a nucleus fissions, the energies involved are measured in millions of electron volts. The ratio is roughly 1,000,000 to 1. Nuclear reactions are, event for event, approximately 1,000,000 times more energetic than chemical reactions. Why the factor of 1,000,000? Because chemical bonds involve the electromagnetic force acting at atomic scales, distances of about 100 picometers, the size of atoms. Nuclear reactions involve the strong force acting at nuclear scales, distances of about 1 femtometer, which is 100,000 times smaller, and the strong force is intrinsically much more intense than electromagnetism at those distances. So you have a stronger force acting at much smaller scales, which means vastly more energy packed into a vastly smaller space. And when you release it, the contrast with normal chemical energy is a factor of roughly 1,000,000. This is physics. This is the universe having layers. You peel back one layer, atoms, chemistry, and underneath is another layer, nuclei, nuclear forces, and the energy scale jumps by a factor of 1,000,000. And when you peel back even further, you find quarks and gluons inside the protons and neutrons, and the energies jump again, and the physics changes again, and we start to see structures that we're still trying to fully understand. The universe is deep. That's the message. Every time we look more carefully, there is more there. Now I want to address something directly. Some of you have been sitting there, and there's a thought in the back of your mind that I suspect goes something like, this is all very interesting, but isn't it dangerous to be talking about nuclear weapons so admiringly? Isn't there something irresponsible about calling the physics beautiful? I want to answer that seriously. No, I don't think so, and here is why. The beauty of the physics and the horror of the application are two separate things, and you can hold both at once. In fact, I would argue that you must hold both at once if you want to think clearly about the problem. If you refuse to understand how nuclear weapons work, if you treat them as simply too terrible to examine carefully, then you are not actually in a better position to prevent their use. You're just in a more comfortable position of ignorance. The people who spent their lives working to reduce the nuclear threat, the physicists who became arms control advocates, the scientists who negotiated treaties, the people who spent decades studying warhead design in order to verify disarmament, they were not naive about the physics. They understood it completely. They understood it completely, and they still concluded that these weapons should never be used. Understanding is not complicity. Admiration for the physics is not admiration for the destruction. The equations don't care how they're applied. Gravity works whether you're launching a satellite or dropping a bomb. The strong force works whether you're building a power plant or a weapon. Physics is not moral or immoral. Physics just is. The morality lives in us, in what we choose to do with what we know. Oppenheimer understood this. Here was a man who spent years of his life leading the effort to build the first nuclear bombs, who watched the Trinity test and said famously, "Now I am become death, the destroyer of worlds," and who then spent the rest of his life advocating for international control of nuclear weapons and was eventually stripped of his security clearance for it. He did not stop understanding the physics when he became horrified by the implications. He held both. He had to hold both. That's what it means to take something seriously. I would rather you walk out of here with a deep, genuine understanding of why these weapons work, the mass energy equivalence, the binding energy curve, the chain reaction, the thermonuclear cascade, than walk out having felt appropriately solemn, but learned nothing. Solemnity without understanding is theater. Understanding is the real thing. And now I want to tell you something that I think is rarely said and that I think is the most important single insight I can give you about this whole subject. The reason nuclear weapons work, the reason there is so much energy available, is a direct consequence of how stable ordinary matter is. Read that again. Let it land. The reason nuclear weapons are so powerful is because nuclear physics arranged itself so that ordinary, everyday matter, the rocks, the air, the water, the bones in your hand, is in a state of extraordinary stability. The strong force is just strong enough to hold nuclei together against electromagnetic repulsion. The binding energies are just right. The masses are just right. And because ordinary matter is so stable, when you disturb that stability under the right conditions, the energy that floods back out is enormous. A universe with weaker nuclear forces would have less stable matter and less powerful nuclear reactions. A universe with stronger nuclear forces might not have atoms at all. Protons might not even be stable. The specific numerical values of the fundamental constants of nature, the strength of the strong force, the electromagnetic coupling, the masses of quarks, these values are, to put it plainly, somewhat suspiciously fine-tuned for the existence of complex, interesting matter. Change them by even small percentages, and you do not get a slightly different universe with slightly different atoms. You get a universe with no atoms at all, or a universe of only hydrogen, or a universe that collapsed before stars could form. Why? Why are the constants what they are? Why does the strong force have exactly the strength it has? No more, no less. I don't know. Nobody knows. Some people think it's a coincidence. Some think there are many universes with different constants, and we live in one where the constants allowed us to exist. Some think there's a deeper theory we haven't found yet that explains why the constants must be what they are. Some think it requires an entirely new framework of thinking that nobody has invented yet. This uncertainty is real. It is not a failure of science. It is the current frontier of science. And I find it magnificent, not frightening, magnificent. You came in here to learn about why nuclear bombs work. But what you've actually learned, if I've done my job, is this. Nuclear bombs work because of properties of nuclear forces that exist, because of properties of quantum field theory that exist, because of the specific values of fundamental constants that govern reality that we don't yet fully understand. It goes all the way down. Pull one thread and you end up holding the fabric of everything. And somewhere in that fabric, in the same physics that made the sun shine and built the atoms in your bones and powered the stars that died to make the heavy elements, somewhere in there is also the capacity for tremendous destruction, the same laws, the same constants, the same universe. This is, I think, the truest and deepest thing I can say about this subject. The universe does not separate the beautiful from the dangerous. It doesn't have a special category for safe physics and unsafe physics. The strong force doesn't know it's being used to heat your tea when it's holding carbon nuclei together in a combustion reaction, and it doesn't know it's being used to level a city when it's being released in a chain reaction. It's the same force. It's the same universe. We're the ones who have to do the separating. We're the ones who have to build the categories of good and evil and decide which applications of which physics are acceptable and which are not. That job doesn't come with instructions. It doesn't come with a formula. It comes with exactly the kind of hard, ambiguous, terrifying moral reasoning that human beings have been bad at throughout history, but that we have no choice but to try to get better at. The physics is not the problem and not the solution. The physics is just the reality we live in. And here is where I want to leave you. There's a gram of uranium, less than a paperclip, somewhere in the world right now, in a nuclear warhead, containing roughly 90 terajoules of potential energy, bound up in the mass of its nucleus, in the strong force holding protons and neutrons together, in the same fundamental interaction that holds every atomic nucleus in your body together at this moment. That energy was there when the Earth formed 4.5 billion years ago. It was there when life first appeared. It was there when our ancestors first looked at fire and wondered what it was. We didn't put that energy there. We didn't create it. We found it. And now we have to decide what kind of species we are, a species that found something extraordinary and used it to understand the universe better, or a species that found something extraordinary and used it to end itself. That question is not settled. It is not history. It is happening right now, today, in decisions being made by governments and laboratories and individual human beings who all contain, in their own nuclei, in their own atoms. The same physics we've been talking about this entire time. The universe gave us the knowledge. What we do with it, that's up to us.